You've learned to solve AX equals B by row reduction, but the question, does this system have a solution, is really a geometry question. Does one vector live inside a specific space? Here's a 4x3 matrix A. Its columns are a 1 equals 1, 2, 3, 4, a 2 equals 1, 1, 1, 1, and A3 equals 2, 3, 4, 5. That's 3 columns living in R4. Rx equals B is solvable only when B is reachable from these columns. And if you look closely, one of these columns is a freeloader. Column 3 is just column 1 plus column 2. Let's make this precise. When you multiply a matrix A times a vector x, you compute x1 times column 1 plus x2 times column 2 plus x3 times column 3. Matrix vector multiplication is a linear combination, a weighted sum, of the columns of A. The entries of X serve as the weights. Let me write it out for our specific matrix. A times X equals X1 times the vector 1, 2, 3, 4, plus X2 times the vector 1, 1, 1, 1, plus X3 times the vector 2, 3, 4, 5. Notice, the vector x does not plug into equations the way you might expect. Instead, x chooses the weights. Each entry of x controls how much of one column gets included in the output. Change x and you change the combination. So solving ax equals b means find weights x1, x2, and x3 that combine a's columns to produce b. If no set of weights works, the system has no solution. This leads us to a key concept, the column space. The column space of A, written C of A, is the set of all vectors you can produce by taking linear combinations of A's columns. Formally, C of A equals the set of all AX as X ranges over R3. Now here's the crucial observation. Every column of A lives in R4 because each column has 4 entries. So the column space is a subspace of R4, not R3. Don't confuse the dimension of the input space with the dimension of the output space. A subspace is a set that is closed under addition and scaling and that contains the 0 vector. You can think of C of A as every possible output of the matrix, the entire collection of all reachable B vectors. Geometrically, picture this as a plane passing through the origin inside R4 with the column vectors lying on that plane. Let's test some specific B vectors to see if they're in the column space. First, take B equals 1, 2, 3, 4. That's column 1 of A. We can set X equals 1, 0, 0. Then AX equals 1 times 1, 2, 3, 4 plus 0 times 1, 1, 1, 1 plus 0 times 2, 3, 4, 5, which gives us 1, 2, 3, 4. This B is in the column space. Check. Next, take B equals 1, 1, 1, 1. That's column 2 of A. Setting X equals 0, 1, 0 works immediately. AX equals 1, 1, 1, 1. Check. Now try B equals 2, 3, 4, 5. That's column 3 of A. So X equals 0, 0, 1 works. X equals 2, 3, 4, 5. Check. But here's the interesting part. X equals 1, 1. 0 also works for the same B. Let's verify. 1 times 1, 2, 3, 4. Plus 1 times 1, 1, 1, 1 equals 1 plus 1. 2 plus 1, 3 plus 1. 4 plus 1, which is 2, 3, 4, 5. Same B, but 2 completely different X vectors, right? 2 different recipes giving the same output. Something suspicious is happening with column 3. Column 3 equals column 1 plus column 2. Let's verify this entry by entry. Looking at the first entries, 1 plus 1 equals 2. Check. Second entries, 2 plus 1 equals 3. Check. So entries, 3 plus 1 equals 4, check. Fourth entries, 4 plus 1 equals 5, check. So column 3 is exactly the sum of columns 1 and 2. Now think about what this means. Column 3 is redundant. Any linear combination that uses column 3 can be rewritten using only columns 1 and 2. Right? Here's how. Suppose we have x1 times a1 plus x2 times a2 plus x3 times a3. Right? Since a3 equals a1 plus a2, we can substitute to get x1 times a1 plus x2 times a2 plus x3 times the quantity a1 plus a2. Distributing x3, this simplifies to x1 plus x3 times a1 plus x2 plus x3 times a2. So if column 3 appears with weight x3, we simply add x3 to the weight on column 1 and add x3 to the weight on column 2, and we get the same result. Column 3 contributes 0 new directions to the column space. It's the freeloader. R has 3 columns, but the column space is only 2-dimensional. It is a plane through the origin inside R4. Right? 3 columns does not automatically mean a 3-dimensional column space. Only linearly independent columns expand the space. Let's verify. Columns 1 and 2 are independent because neither is a scalar multiple of the other. If A2 equals some constant C times A1, we would need C equals 1 from the first entries, but C equals 1/2 from the second entries, a contradiction. So they are indeed independent. Column 3, however, is linearly dependent since A3 equals A1 plus A2. We call the independent columns pivot columns. So columns 1 and 2 are pivot columns, while column 3 is a free column. Now let's summarize the key properties. The number of columns of A is 3. The number of independent or pivot columns is 2. The dimension of the column space C of A equals the number of pivot columns, which is 2. The column space lives in R4 since A has 4 rows. And since 2 is less than 4, AX equals B is not solvable for every B in R4. The dimension of C of A equals 2. Since the column space of A is a 2-dimensional plane sitting inside R4, most vectors in R4 don't lie on that plane. Let's find one. Take B equals 0, 0, 0, 1. We need x1 times the vector 1, 2, 3, 4 plus x2 times the vector 1, 1, 1, 1 to equal 0, 0, 0, 1. Remember, only columns 1 and 2 matter since column 3 is redundant. Row 1 gives us x1 plus x2 equals 0, so x2 equals negative x1. Row 2 gives us 2x1 plus x2 equals 0. Substituting x2 equals negative x1, we get 2x1 minus x1 equals x1 equals 0, and therefore x1 is 0, and x2 is also 0. Now let's check row 4. 4 times 0 plus 1 times 0 equals 0. But we need it to equal 1. 0 does not equal 1. And that's a contradiction. There is no solution. The vector 0, 0, 0, 1 is not in the column space. Geometrically, it floats off the plane. Here's the full picture. Every time you ask, can I solve AX equals B? You're really asking, is B a linear combination of A's columns? The column space C of A is the complete answer to which right-hand sides are achievable. The dimension of the column space has a special name, rank. Rank equals the number of pivot columns. Our matrix has rank 2. Now here's an important case. If the rank equals M, the number of rows, then the column space C of A fills all of Rm, and AX equals B is solvable for every B. That's called the full row rank case. But our matrix has rank 2 with 4 rows, so most B vectors in R4 are unreachable. One question remains. When AX equals B is solvable, how many solutions exist? Remember, we saw 2 different solutions for B equals 2, 3, 4, 5. The null space answers that question, and it's the subject of the next video. Think of it this way. The column space is the menu of achievable outputs. If B is on the menu, X is the recipe. The null space tells you how many recipes exist.